my name is James Buck, and I'm here to talk to you about algorithms, the joy of algorithms. You're going to be riveted. You're going to be so excited coming out of here. We're going to pound more code after this session than has ever been pounded at RubyConf. Now, what I want to talk to you about is getting better at something, whether it's running or walking or crawling or dancing or singing or drawing or cooking or programming, no matter what it is. The process of going from where you are to where you want to be involves hard work, okay? That's the secret sauce. It's hard. Yeah. Interlude. And I don't dance, so it would be hard work for you to watch me dance, okay? That's the secret sauce. That's the silver bullet. There's not an easy way to get good at something. You just have to work hard at it. Now, the thing about hard work is it's hard work, right? Sometimes we don't want it to be hard work. We sit down and we get frustrated when we want to learn something and it's not easy. But we need to accept that it's hard and go forward with it. We need to work the parts that are hard for us because that's what will make us better. When we work the parts that are easy for us, that's play, okay? And there's a place for that because it keeps us fresh. It keeps us able to do the things we do regularly. But play is not exercise. Play is not hard work. And it's the hard work I want to focus on. Now, one of the key things about hard work, seriously, the thing about hard work is you need to work at it regularly. You know, consistent, regular exercise and a schedule is what will help you improve. When you don't stick to a schedule, things kind of fall apart. I mean, it can still help. It's better to do it once in a while than not at all. Like if you're trying to learn to program, it's better to sit down in front of the computer and try something once in a while. But it's even better if you sit down in front of that computer on a regular basis and force yourself to do something new, something that's not in your comfort zone. Now, you don't want to sit down and solve an NP hard problem, right? You need to focus on something that's within your range that you can reach. But still, stretch yourself. Go a little bit outside your comfort zone. Now, the thing about the regular, consistent schedule is that's all time management, and I don't want to talk about that. Time management does not interest me at all. What interests me is the plan, the steps you will take to get better, okay? And along those lines, I want to talk to you about algorithms, because algorithms, I think, are one of the perfect tools you can use as a programmer to get better at your craft. Okay? I mean, what is an algorithm? An algorithm is a step-by-step description of what you need to do, right? It takes you through the process of accomplishing some task. And that's why they're great. But the cool thing about algorithms is that they're everywhere, okay? In computers, you seriously can't turn around without bumping into an algorithm. No matter what you do day to day as a software developer, you are using algorithms. And algorithms, there's easy algorithms, there's hard algorithms, there's algorithms that you use all the time and algorithms that you've never heard of before, and everything in between. There's a huge range of possibilities for you to investigate, which is another thing that's awesome about them. And for me, I really enjoy maze generation algorithms. How many of you followed my blog a year ago when I was writing about that? Good, so a lot of this will be new to people. The rest of you, it's review. No. A maze really is just, it's the puzzle where you start at some point and you go through the maze to the other end of the point, and as long as you don't cross any lines, you win. But the cool thing about it is it's also packed with graph theory. And graph theory is fascinating, and it has so many applications in computer science. Now, my personal interest in mazes are the class of mazes called perfect mazes. And these are mazes that have one unique solution. There is no cycles in the maze. You just find your way through it, okay? And it's what most of us think of when we think of mazes. Now, a maze is a spanning tree. A perfect maze is a spanning tree. And spanning trees are a very well-researched and very well-documented data structure for which there is a huge body of algorithms available. And now you're sitting there glaring at me and saying, wait a minute, I didn't sign up for a computer science lecture. And I'm saying, surprise, you totally signed up for a computer science lecture. But that's not a bad thing. If you want to get good at chin-ups, right, you're going to do a lot of chin-ups. But if you want to get in shape, you're going to do chin-ups and sit-ups and push-ups and running and a lot of other things. It's not just about the chin-ups. The same is with computer science or with programming or anything you want to do. If you can cover a wide base, you're going to make yourself more able to learn more. By learning these new concepts, you add these little hooks in your brain that you can hang stuff on. And then when you encounter another idea, those hooks are already there for you. You can say, wait, that's just like this other thing I learned about. Okay? If you look at graphs and you're like, yeah, there's this little dot thingy and then a line, it's really hard to talk to other computer scientists about it because a dot thingy and a line can mean a lot of different things. But if you're talking with the same vocabulary, things get a lot easier. So we're going to start with a basic vocabulary lesson. We're going to look at this, okay? In graph terms, this is called a vertex or a node. I'll sometimes call it a cell. And it's represented as a dot. But it can really be anything. It can be a car. It can be a person. Like in data modeling, it might be the people that are friends and so forth, okay? This is an edge, and it's usually represented as a line between two nodes. And it represents a relationship between those two nodes. In a maze, that's going to be a passage between two locations. But in a database, it might be, is a friend of this person. It represents some relationship between two entities. Now, when you get a bunch of nodes and edges all together, that's a graph. And in this case, if every node is reachable by every other node in the graph by following one or more edges, then you've got a connected graph, which is what this is. And this is also a graph with a cycle in it, which means it's got a loop. Okay, you go round and round and round. If we cross out one of those edges and break the cycle, we now have what is called an acyclic graph. And this happens to be a connected acyclic graph, which is the same thing as a tree. And trees we deal with all the time in computer science. Now, any given graph can contain multiple trees at the same time. A tree doesn't have to span the entire graph. But if it does, we have what is called a spanning tree because it spans the graph, obviously. And spanning trees are cool because they are those perfect mazes that I was talking about. Now, fortunately for maze lovers, any given graph contains multiple possible spanning trees, okay? And that group of spanning trees is called the spanning forest. And so what the act of maze generation is, it's simply going into that spanning forest and plucking one of those spanning trees out and saying, here's my maze, or this one. And ideally, if you can do that uniformly, like with no bias, no prejudice, just randomly and evenly distributedly, evenly pulling those things out, the result is called a uniform spanning tree. And there's nothing that you can look at and say, this is a uniform spanning tree. It's a statistical entity. But it's kind of the holy grail of maze generation, is a uniform spanning tree, to be able to pull it out and have no bias and be perfectly random. The question is, how do you get these mythical beasts, okay? These uniform spanning trees, and that's where things start getting interesting. Aldous and Broder were two researchers who were studying this problem, and they came up with a solution, an algorithm, yes. What they said is, well, if you start anywhere in this graph, that's your starting point, and then you do a drunkard's walk, okay? You just start going node to node through this graph, visiting as you go. By the time you've visited all the nodes, you'll have a uniform spanning tree. Specifically, if as you go, when you move from one node to another, if that other node has not been visited yet, you connect them, draw a passage between them in maze terminology. But if you go from one node to another and that one's already been visited, then you don't do anything. As long as you obey those rules, by the time you've visited all the nodes, you'll have a maze, in my terminology. So let's take a look at it. Let's run one here quick. La la la, and it finally gets around to finishing it up. Let's do that one more time just so you can be totally bored. See how it just kind of goes and does its own little thing? That's because it's not intelligent, right? It's just following the rules of blindly walking that graph. Which the downside is that it's theoretically possible for this algorithm to never complete, right? If it's purely random, then there is a chance that it could go back and forth forever between two nodes and never actually visit the entire maze. And that's bad if you actually want to generate a maze. You'd like some guarantee that it will eventually complete. So this one is slow. It is guaranteed that if it completes, it will give you a uniform spanning tree, but we'd like a little more of a guarantee than that. So Wilson went along and he said, well, maybe there's a way to speed this up a little bit. And his approach was that we're going to start somewhere and we're going to put out feelers, okay? We're going to add one node to the spanning tree, And then we're going to choose another place, and we're just going to try and feel our way to that one. Okay? And when we find it, we're going to do our drunkard's walk as we attempt to do it. And when we get there, when we find a connection between those two, we'll draw the path. We'll add that path to our spanning tree. Then we'll do it again. We'll pick some other node that isn't part of the tree, and we'll just do our random walk until we encounter a node that is in the tree. And we do that over and over and over until everything's been visited. Now this works a little faster than Aldous-Broder, because after that first walk, where it has to go from one place to find the needle in the haystack that's already in the tree, after that you've added a bunch more nodes to the tree. And so the next walk has a much greater chance of finding one of them, and the walk after that a much greater chance, and so forth. And so it snowballs and gets much faster. Let's take a look here. See, at first, and there it just picks right up and goes like crazy. Let's do it one more time. You can see it walks for a while until it finds what it's looking for, and then it gets there. So that's Wilson's algorithm. But because it's doing that random walk that can go anywhere, it suffers from that same problem of Aldous-Broder, that there's a chance that it may never complete. And that's not cool. So this one is slow as well. But if we don't mind farming from a particular corner of that spanning forest, right? If we don't mind that there might be a bias involved, we might get mazes that are all long and twisty passages, or that have a lot of dead ends, or things like that. If we don't mind those kind of biases, then there are ways to do this faster. The binary tree algorithm is one of those algorithms. It's very fast and very biased. The reason it's fast is because it can do the entire graph in order n time. It only has to look at each node once. And it makes one decision for each node. It says, do I connect a passage north or do I connect a passage west? Once it makes that decision, it moves to the next node. So you can just fly through this algorithm. There's an example. Now, you can see there's kind of a strong lean to the maze, right? It tends to have this river heading towards the diagonals. There's also a solid corridor on the north and a solid corridor on the west. And those are all side effects of the algorithm. Okay, we've farmed this particular maze from a particular corner of our spanning forest, right? And in this corner, all of the mazes have a solid corridor across the top and a solid corridor on the west. We can switch things up a little bit. For instance, we can say, what if we choose south and east instead when we run it? So if we choose south and east, then it just changes where that bias is located. But the maze still has that very strong bias. The nice thing about this is if you're in that corner and you're trying to get to the other, it's trivial, because there's no dead ends if you're going from one diagonal to the other. But if you're going the other way, then it gets harder because there's more dead ends. So there's some bias in that one. So let's take a look at the Sidewinder. This one has the potential to get rid of some of that bias. The way it works, I mean, you looked at the binary tree algorithm, right? And it looks at each node in isolation. It says, okay, what are you going to do, buddy? And you are going to go north, or you are going to go west, and that's the way it is. Sidewinder goes row by row, just like the binary tree algorithm did, but this time it groups adjacent nodes into clusters, okay, into random groups, and it'll say, okay, this guy's by himself, and these next two are together, and these next three are together, and this guy's by himself, and so forth. And then it looks at those groups and says, from each of those groups, I'm going to choose one member to carve north. And when we do that, see, there's no longer that strong lean anymore, but there's still a solid passage across the top because you can never carve up from a cell that's already at the top, so you just group them all. And just try it with your eyes here. Pick any cell on the bottom and try and find your way to the top. It's trivial. Like, again, there are no dead ends when you move bottom to top. There are dead ends when you move top to bottom, though. So in situations where that's the direction you need to go, this may be a very appropriate algorithm for you. Okay, so that one has some bias too. So what can we do? Well, we can look at Aldous-Broder and Wilson's algorithms and say, well, what were they doing that these other algorithms weren't? And one of them is, well, they were doing that drunkard's walk, right? And say, well, maybe there's something to that. What if we try that? Oh, I got ahead of myself, sorry. There's one more we're going to do that goes row-wise. This one's actually really tricky. This one took me a long time to wrap my mind around. Even though it looks like visually like it should be simple, it works a lot like the Sidewinder in that it groups horizontal clusters of cells, but this time it groups them into sets where they may not be adjacent cells. Like you may have this one in set 1, and this one in set 2, and this one in set 1 again. In this case, we've got 2 adjacent cells that are in different sets, and we're trying to decide if we want to merge them. We'll say we do. We merge them. The next step is you say, okay, we're going to create at least one downward passage for each group of cells, each set, not group of cells, each set on this row. And in this case, we create one, and we merge that one then into the same set. Then we increment the row. So then we go down to the next row and we do the same thing. But this time, some of the sets are already done for us. They're part of that, the previous row, or the previous rows. And that's where things get tricky. You have to keep track of which set each cell is in. But the result, as it goes down, it's a lot less bias. Like you look at this, you don't immediately see the biases that you saw in the binary tree and the Sidewinder. It does have a tendency to create a long passage on the bottom. That is probably its weakness, because it has to combine all the sets into one by the time it finishes. And it usually tends to do that last minute. It gets to the bottom and says, oh, crap. And it combines everything all at the last minute. You got this one long passage. But other than that, the mazes it generates are pretty great. Okay, so now we're to the Drunkard's Walk one. What happens when we go with Drunkard's Walk? Hunt and kill is one such algorithm that's based on the Drunkard's Walk. And it works in 2 phases. The first is the kill phase, where it tries to swat as many cells as it can, doing a Drunkard's Walk. Just teeters along, follows that Drunkard's Walk into any cell it wants, with one condition. This time it adds a constraint, so that we make sure that we can eventually terminate. The problem with Aldous Broder and Wilson's is that they have a chance of never terminating because they can go back and forth. This time we say you can do a Drunkard's Walk anywhere you want as long as you only visit cells that haven't been visited yet. And so that way it can never go back to where it was. It just snakes on and on. But because we've added that constraint, it can now walk itself into a corner, right? It can go around on itself and dead end. So what do you do in that case? The hunt and kill algorithm in that case enters hunt mode, okay? That's where it says, oh, we're done killing. Now we need to look for more to kill. And so it goes up to the top row, and it starts scanning row by row for any cell that hasn't been visited that is immediately adjacent to a cell that has been visited. Okay? Once it finds that particular configuration, it goes back into kill mode. It connects those two, goes back into kill mode, and starts doing the random walk again from that unvisited node. And with that addition, you're guaranteed that it will complete. Because when you do a final scan, when you hunt, and you don't find anything that's unvisited, then you know you're done. So let's take a look at that one. So it snakes around. You can see it doing its quick scan there, and then does a final scan, and it's done. One more time. And there it's done. So that's cool. That's possibly an improvement. It's still biased. The bias on this one is it's got long, windy passages with few dead ends. Okay? Because we're sacrificing dead ends for longer passages. We're just winding as far as we can before we dead end, and then we go as far as we can before we dead end. I kind of like that bias personally. I like the look of this kind of maze. But it does tend to create mazes with simpler solutions. Because there are fewer dead ends, there's fewer chances of going wrong. This one's also slow, right? Not as slow as Aldous Broder or Wilson's, but scanning the entire graph over and over and over again is not a cheap operation. You're looking, that right there makes it an order n squared, right? The big O notation. So what can we do? Well, let's try another tack. What if we do our random walk, but we keep track of where we've been? We keep a stack, and every time we visit a node, we throw it on a stack. We visit one, we just keep throwing it on there. Then when we dead end, we start popping those babies off until we get to a node that has an unvisited neighbor, at which point we can start our random walk again and throw some nodes on there again. So we throw the nodes on, pop them off, and when we've popped all the way back to the very beginning and our stack is empty, that's when we're done. Because we know that we've tried every possible node and none of them have any unvisited neighbors. Therefore, we're finished. So this one is one of my favorite to watch. Just snakes around until everything's done. Still, it has the same bias as hunt and kill, right? Because you're still doing the long passages and sacrificing the short dead-end corridors. Now, since we're talking about recursion, here's another really cool algorithm that's actually very different from any other maze algorithm I've seen. Whereas most maze algorithms I've talked about and researched work by carving through something. You can think of like you're in a mountain, you give a dwarf a pickaxe, and off he goes chipping his way through carving passages, right? The recursive division algorithm actually says, well, no, we're going to be calm, and we're going to have a nice, big, peaceful field, and we're going to build walls all through it. So it's a different way of thinking about the problem. What it does is it gives you that empty plane, and then it chops the field in half. Okay, and then it creates a passage between the two halves, and then chops those halves in half, and then creates passages there, and then chops in half, and you just keep chopping in half until you get down to the resolution of your passageways, and then you're done. Like this. It's a lot of fun. This is actually a fun one to step through. Let's go step at a time. So you start with your full field, and you cut it in half, and then you add a passageway connecting the two. Then you choose one of the subfields, and you cut it in half. You create a passage connecting the two, and then you choose one of those subfields. And you just keep doing it recursively, the same process. 1, 2, 3, 1, 2, 3, 1, 2, 3. And when you get down to the resolution you want, then you pop over to some other subfield that hasn't been divided far enough yet, and you let it go. So that's the recursive division algorithm. And one nice thing about this one is you can actually control how far down you go. You don't have to go all the way down to the resolution of the passages every time. If you stop early, you wind up with rooms, okay, larger areas that are then connected to other parts of the I want to say dungeon, because that's what comes to mind, other areas of your maze. But it's biased, okay? It's biased too, because if you look, if you're trying to go from the top to the bottom, we cut the entire field in half and created one passage, right? So you know that if you're going north to south, you have to go through that bottleneck somewhere. There's lots of bottlenecks in this kind of maze, which means you wind up with mazes that are fairly straightforward to solve. It's never going to do these big up and down and back and forth. Yeah? Oh, yeah.
How do you chop a graph?
You don't chop the graph in half. What you do is you build walls. In other words, you start with a fully connected graph, and you pull edges out. And then you connect them again where your passage is. And then you pull edges out. And anyway, yeah. Now, actually, under the covers, I mean, that's how you would think of it as a graph. But if actually under the covers implementing it, it might be easier to implement it some other way, like with an array, right? With a two-dimensional array. But yeah, it's still graph theory. Okay, so now we've explored a few different options. What if we say, well, obviously spanning trees are a very well-researched, well-documented area. Surely others have solved these problems before of taking a graph and finding a spanning tree for it, and of course people have. If you have a graph with weighted edges, in other words, there's a number on each edge that tells how expensive it is to cross that edge, then you can take an algorithm like Kruskal's, which finds a minimum spanning tree and run it on that. And what it does is it tries to find the spanning tree with the lowest cost, okay, by finding the edges with the lowest numbers that still make a spanning tree. But now, if you, instead of weighted edges, what if you just throw random numbers on all of them and then run Kruskal's? Well, what you get is a random spanning tree, okay? Still with some bias, but it works. And conceptually, the way I think of it is like a field of Play-Doh balls, right? And as you go through this field, you start connecting adjacent pieces of Play-Doh, with the constraint that you can never connect two adjacent pieces of Play-Doh if they are already connected somehow. So that piece in the upper left corner there, we couldn't connect the bottom two because there's already a path between them. But we could connect the two in the middle on the right, okay? You just keep doing that until all you've got left is one big piece of Play-Doh strung all over the field. And when you've done that, you've got your spanning tree. Kruskal's itself doesn't do a whole lot for me. I mean, it's kind of fun to watch how it appears out of nothing, like just little pieces here and there all kind of coming together. But what I love about Kruskal's is this. If you start with a configuration like this, where you've stretched the Play-Doh across the middle, across 3 nodes, and then you've taken another piece of Play-Doh and stretched it underneath that one, okay? It's all still disjoint sets. But what happens when you run Kruskal's on that configuration? Well, what you get is a weave maze where the passages go over and under. And you get some really interesting configurations that way. If you start by just putting up your crossings and you make sure that the sets are all valid, and that's kind of tricky in and of itself sometimes. Once you've got that, then you just run Kruskal's. And don't get tangled. And there's you've got your weave maze. But the cool thing is by changing the density of that initial configuration of crossings, you can change how thick your maze is, like how many crossings it has. Those weave mazes, I just love. It's such a great visual representation. It's great to look at. Okay, so Prim's is another one that solves the same problem as Kruskal's. It creates a weighted spanning, a minimum spanning tree from a weighted graph. Yes, sir? Sure. Where would you like it to enter? Pick one. And then pick one that, or anyone you want to be the exit. Okay. Yeah, sure, and it can. But that's the thing with a perfect maze. Because this is a perfect maze, which means between any two nodes in the graph, there is exactly one path. Which means I could choose the top left and the bottom right, and I am guaranteed that there is a path between them. I could pick any two nodes inside the maze, on the edges, anywhere I want, and I'm guaranteed a path. That's why perfect mazes interest me. Because the actual entrance and exit is boring. It can be anywhere you want. You just pick them. Okay? Does that make sense? It is true. These are deceptive to look at, right? You look at it and you think there's no way that's all connected. But I defy you to find a path that does not connect to any other node in that. Okay? We're not going to stand here while you try and defy me. But feel free to shoot me an email if you find an exception. But it is all connected. And watch, let's do this. These crossings are not all connected, right? I think we can agree on that. Because I've thrown them in there at random. Some of them are like long, windy passages through there. Others aren't, okay? But they don't all connect. But what Kruskal's does is it takes disjoint sets, okay? Does everyone know what I mean when I say disjoint sets? Sets for which there is no overlap, for which there are no elements in common. It takes these disjoint sets and makes of them a single set, okay? That is what Kruskal's does. And so when I run it, it just starts taking all of those sets, including the crossings that I made, and bringing them all together into one set. So that when I'm done, I'm guaranteed to have a single set, okay, from which that everything there is a part of. Hope that makes sense. Prim's, like I said, does the same sort of thing, but it approaches it differently. Whereas Kruskal's kind of does something here and then something here and something here, and just magically everything comes together. Prim's actually chooses a starting point, kind of a seed, adds it to the spanning tree, and then takes all of its neighbors and marks them as frontier, okay? They're the wild frontier. The next pass and subsequent passes look at that frontier set, grabbing one at random from the frontier, connecting it to the adjacent node, the visited node that it's adjacent to, and then marking its unvisited neighbors as frontier cells. And it does that over and over and over until there are no more frontier cells, okay? And the way this one works, it reminds me of setting a piece of paper on fire. Because it starts at one place and it kind of grows outward, kind of growing it organically. It's a fun effect, especially on a large maze where the animation runs quickly. It kind of just blows up. Let's watch it one more time just because it's fun. Just because I can. So that's Prim's. And you can do over and under weave mazes with a lot of these different algorithms, I should state, but Kruskal's is by far the most well-suited to that. Okay, the growing tree is probably my favorite algorithm because it can be customized to act like other algorithms. It's like the mockingbird of maze generation algorithms, okay? The way it works is there's nothing remarkable about the way the algorithm actually proceeds. What you do is you take any node as your starting point, and you put it in a set. We're going to call it the active set. Then, at subsequent passes through the algorithm, you look at any node in that active set, and you find its adjacent neighbor. You look at its adjacent neighbors, and you pick one at random, and you connect them, and then you take that neighbor, and you throw it in the active set. Now, if that node had no unvisited neighbors, then you would remove it from the active set. Okay, so that's how the algorithm terminates. It goes until there are no more nodes in the active set. But as long as there are nodes in the active set, you pick one out, you look to see unvisited adjacent neighbors, you connect to one of them, and you throw that neighbor into the active set, and you just keep doing that over and over. There's nothing really exciting about how that works. But what interests me is this, like how do you choose something out of that active set? Changing how that works changes the whole behavior of the algorithm. For instance, if you always grab the node that was most recently added to the active set, so you put one in and you immediately take it out again and look for adjacent neighbors to that one, you get the exact behavior of the recursive backtracker, okay? Because it's a stack. You put it in, you pull it out, you put one in, you take it out, you just keep building on top of that. On the other hand, if you grab at random, so you put one in and then you shuffle the bag and you take one out, you have something very similar, though not identical to Prim's algorithm, where it starts at a seed and it just starts growing out. So let's take a look. Here's the growing tree done as taking newest from the active set. And you'll see it acts exactly like the recursive backtracker. There's no way looking at just an animation of the algorithm to say whether it was growing tree newest first or recursive backtracker. On the other hand, if we take Prim's, not Prim's, but choosing randomly, we get something that's very much like Prim's, where it grows outward until the whole maze is done. But the cool thing now is what happens if half the time we choose the newest from that active set, and the other half of the time we choose at random. Okay, if we go 50-50, we get kind of a fusion of the two algorithms, where it tries to go, random walk, and then it jumps over here and does a little random walk here, and it jumps over here until the whole maze is fleshed out. And that gives you, that kind of tries to mitigate the long winding passage bias that you get in recursive backtracker, right? Because now it goes, but then it jumps somewhere else. Like it'll abort that random walk and go try to do it somewhere else. And you can do like a 25-75 split if you want. So we're favoring the random on this one. Now what happens if we always choose the oldest node in that pack? Pretty exciting. It's interesting, not the most exciting maze in the world. But what's interesting now is what if we take that and combine it with one? So we take oldest to newest, 50-50 split. Okay? And you get this interesting fracture pattern where it looks like you've shot a bullet at a piece of glass and the passages just kind of all go out from there. You can do the same thing with the random, so oldest and random split. But you can combine these in all kinds of ways. Like you could have 1/3, 1/3, 1/3 split with newest, oldest, and random. Okay? Or you could weight random a little heavier. In other words, you can tweak this to get almost exactly the effect you want. Okay? It's really, really quite fun. Now, just for grins, I want to talk about one more algorithm. Okay? Those 11 I just talked about are the ones I mentioned on my blog, and which I think will do you a world of good to actually try implementing. This last one is called the growing binary tree algorithm. And I stumbled on this one. I won't say I discovered it because that is way too, that's overstating it by a lot. What I did basically is as I was playing with the growing tree algorithm, I thought, what, instead of choosing one adjacent neighbor and putting it in the active set, what if I choose two and put it in the active set? Okay? And instead of keeping that node in the active set when I look at it, what if I take it out and remove it and then add the two neighbors? And when I do that, it's still growing tree algorithm, so I can still choose to take newest first or random or whatever. Using newest first, I get this kind of effect, where you get the long, windy passage, but it's kind of hairy. Okay? It's got all these short little passages branching off of it all the way around. And interestingly, if I do random first, you don't get that hairy effect. Okay? It's basically just like Prim's, but moving twice as fast because you're throwing more nodes out there. And of course, you can do any of these others just like you can with a growing tree. But the point that I want to make is not so much that, ooh, gee, how cool is this algorithm? It's, look what happens when you take things that you know and combine them. That way you start playing with these algorithms as you've learned them. Okay? You start pushing that envelope back a little bit and you say, oh, that's a cool effect, and this is a neat idea. And it's stuff that may not be documented anywhere because there's so much that you can learn and discover that not everything has been documented yet. It's all about hard work. That is the real point here. It wasn't easy for me to learn all of these algorithms, but I'm so glad I did because they've been a blast. I've had so much fun with these, and I've gotten so much mileage out of them. And it's a great tool. Once you are familiar with the algorithms themselves, are you done? No. I mean, just because the algorithms themselves are no longer a challenge doesn't mean they can no longer offer a challenge. Try implementing them in a framework or a language you're not familiar with. Like, how many of you would say you are comfortable in a functional language? A few of you, very brave of you. I am not. I'm not comfortable in functional languages, but I'm trying to be. And I tell you, I can implement these algorithms almost in my sleep in Ruby, okay? It is extremely different implementing them in a functional language because you have to think about them in an entirely different way. It's the same algorithm, but completely different way of approaching them. So just because you've mastered something in one field doesn't mean it can no longer offer any challenge. The goal ultimately is to look for the resistance, okay? Look for the pieces that are going to offer the most resistance because those are what you need to push against in order to make yourself better. If you want to be a better programmer, you must work at it. It's not going to just happen. And your day jobs are very often, I won't say never, your day jobs are very often not enough resistance, okay? What you do every day is stuff that you do every day. And once in a while, there will be some new problem that you have to solve. But I would strongly recommend you think about finding time to do homework, to exercise it. Thank you very much.